This is Terry at Sirius, and we're going to talk about in this video application note the raw transport protocol, now coming in SHIP version 5.0.126. There are three data communications protocols supported by SHIP, and your GUI needs to communicate with the outside world. And there are two types of communications that you're going to generally want to do. One is to exchange data back and forth between the SIM and running the GUI and the SHIP engine over a UART or SPI port, for instance, out to some attached device. That's your microcontroller running your machine, pumps, motors, valves, whatever it is. And you're going to be connected, for instance, over a UART. We're going to be communicating and exchanging data, like the door is open, the pump is on, the RPM of the motor is 5,400. These types of things are the data that you're going to exchange back and forth. There's a separate video application note if you look up data transport models and get into more detail about why it's important to exchange data and not have your back end understand what's on the GUI specifically. There's a very big philosophical difference and two different ways of approaching the problem. We have a strong bias towards data movement and not GUI instruction movement and GUI knowledge in your system. But that's a separate topic. What I want to talk about today is the raw protocol introduced in 5.0.126. Now, there's three different protocols that SHIP supports. At the very low end is the raw protocol. That is moving a byte back and forth, a word back and forth, a string back and forth. There is no framing, there's no error detection, and so there's a lot of disadvantages to raw. On the other hand, if you're doing something very simple, sometimes the raw protocol is just the easiest way to get a demo up and running, and maybe you don't want to use that forever because of the lack of error checking and things like that that's inherent in a raw protocol. But it sure is easy sometimes to get a demo up and running where you send a byte out and your microcontroller on the other end of the wire is getting a letter, O, and then you open the door, C, and then you close the door, that kind of thing. Great fast demos, easy to do. You don't need to actually create any kind of protocol driver on your microcontroller. Probably not where you want to stay long term. You probably want to upgrade to the second protocol, Modbus, which has packetization and error checking, or you want to go to the third level, SHIP Bridge, and the Bridge protocol coming in more completely in 5.0.200 will not only support all kinds of very sophisticated data push and pull models, but also upgrading over the wire of the complete unit and accessing all the file systems and drives on a SIM. So SHIP Bridge is very sophisticated. So you got three levels: raw, Modbus, and then SHIP Bridge. Today we're going to talk about raw. So raw is new with 5.0.126. You need SHIPTide 5.0.126 and beyond, and you need SHIP Engine 5.0.126 and beyond. So to create, let's just create a new project. Hopefully you're really comfortable with creating a new project now. Let's do that for the SIM 115, for example. And we're going to choose a raw app note. And we're going to say this is a variant, let's say A01. And we're going to choose a very minimal GUI here. Okay, so we've got a 115, little 3.5 inch screen. And the screen, the template, of course, is very, very minimal, just a icon and the background. Okay, now like all communications, you have to set up a link. So let's go over into the resource area and click on links. There are no links created yet. Let's add a new link, and what we're going to do is we're going to bind a communications port, in this case UART0, with a protocol, in this case the raw protocol. So I'm going to call this my link, and notice that we have raw, Modbus, the four different Modbus flavors, and bridge. We're going to choose raw, and we're going to bind it to UART0. 5.0.126 supports UART. The SPI and I2C are not available in 126. We're looking at SPI support later on in an upcoming release. So my link is a name of a link that binds the raw protocol to the UART. Once you've done that, you can't use this UART for any other protocol. It takes over the UART and says we're going to run the raw protocol on that UART. Now this UART is the one that comes off the back connector, the wire harness connector, on all of our SIMs. So all of the Sirius SIMs have a UART that comes off the back connector. Okay, So let's say we've created the link. Now, when we do that, it automatically, unlike the other types of links, it populates a whole bunch of stuff automatically that you can't change here. First of all, it creates a link set called raw. Since this is a point-to-point protocol, not multi-drop, there's only one endpoint. Some protocols like Modbus, you can have multiple devices out on the network, and so there are different link sets for the same link, one per device that's out on the network. In this case, it's one-to-one, and it's hard-coded, and it's called raw. You can't change that. Underneath the raw link set, there are a bunch of constants that you can use in your scripts: added, empty, full, overrun, removed, underrun. We'll talk about those in a minute. And then there's 4 link variables. The iData, that's input data. So when you get data in from the raw port, it comes in on the iData variable. iState, which tells you the state of the input queue. So you'll get events on iState. You'll get the added event, empty event, full event, overrun, removed. And since it's an input, you could get underrun if you read it and there's nothing in there. So you'll get states that happen and events that happen on iState depending on what's happening with iData. So when something comes into iData, a byte comes into the UART, let's say, and you're using bytes, you'll get an added message on an added event on iState. If it keeps coming in and you don't take anything off, you'll inevitably get a full, an added, then a full. And if you get another one, you'll get a full. You'll get an overrun message. You won't get the added full. You'll get an overrun because it overran the queue. Similarly, there's the output data, which is where you put data to go out the wire. You write this variable. You just assign the variable, and the data goes out. When you assign the variable O data, you'll see the state change to, you'll get an added event, and you should get a removed event as the queue gets emptied as well. So you can actually count how many you put in and how many go out. You don't know how big the queue is, that depends on what platform it is, but you'll know when it becomes full, when it becomes empty. You can get all those events. Now, the question you have is, what kind of data do you want to send out? It always has to be the same type, because there's no packetization, there's no framing, there's no context for sending bytes now and then, let's say, 16-bit values next, because how is the other end going to know that this time it's a byte and next time it's a 16-bit value? It's just bytes. So on the output data, your first decision is to choose the output data type, and you can choose byte, 16-bit short, Boolean, which is just a byte, but it helps you keep it straight when things are Booleans, integer, string, and float, and that's 32-bit float, single precision. So, or you can send strings. So all of these, byte, short, Boolean, that's 1 byte, integer is 4 bytes, float is 4 bytes, string is variable length and ends with a null termination. So that's a variable length output. But once you choose this, let's say we choose byte, now your output data is always bytes. If you choose integer, whenever you assign a value, let's say 54, to the OData link variable, it will send out 54, but as a 4-byte integer quantity. It will always be big endian. So watch that. For better or worse, communications protocols are almost universally big endian, and we stuck with that. So this sends out an integer, a 4-byte integer, and all the numbers are signed. But of course, you can choose to work around those issues if you want. I mean, you can treat them as unsigned if you want on your side. But within SHIP, all integers and number values are always signed. So you can send out a 32-bit value, a floating point value, and a string. If you assign OData a value like hello, it will send out HELLO with a terminating 0. Don't forget that all strings within SHIP are UTF-8. So not one character doesn't necessarily mean 1 byte, but for the ASCII character set it does. But if you send out a Japanese string, it will go out correctly. You will see a UTF-8 string go out and a terminating null termination. So on your receiving end, on your micro, you're going to want to accumulate bytes until you see the 0, and then you go, okay, I got my string. Now, the same thing happens on the input. You have to define what we're going to see on the input. And so let's set the data type to string. Okay, the data type now says that the engine underneath, ship engine, will automatically accumulate bytes until it sees a null termination, in which case it will deliver that data to iData and generate an event on iState that says added. And then you can pull the data off iData and retrieve the string. So you can, for instance, say that I'm receiving strings through iData and I'm sending bytes. So I could say let's say we had a little translator in your micro. I could send a short which says I want message number 35, so you send out 35. And it comes back on iData with the message from your device. Hello. There's infinite possibilities. You know what you're trying to control. Now, so how do we wire this up? Well, first thing you're going to want to do is add a listener at the very top level. This is very common when you're using communications. So let's add a listener, and we'll listen to ship launch, which is the launch event when the GUI comes up. And then, of course, we'll add a script. And in this script, we need to configure the UART. So the UART is platform.uart0.parity equals ship UART flags dot parity none, like that. Platform.uart0. Bits, that's your stop bits. I think that's, I'm trying to remember what it is. There it is, stop 1. So, that's your stop bits. So I want that's your stop bits. So let's do 8-bit data. I would not recommend 7-bit data, but you can do it if you want. Okay, so where do you get those from? Well, you go onto you go www.mysiriusintegrated.com, /docs and search for GRM, the Gui Reference Manual. And in the Gui Reference Manual, we list all the platform variables that control I/O for your 231, for your SIM 535, whatever it is, okay? So that's where you get all these values, and you can figure out what's on your platform, how to control the LEDs and the piezo buzzer and all those kinds of things. So the GRM has this. I'm trying to do it from memory here. Now, the other thing, of course, you need to do is set the baud rate. Platform.uart0.rate equals 115/200, let's say. And then we need to enable it. So let's enable the UART. Platform.uart0.enabled equals true. Now let's enable the protocol. So it's important that we enable the link and the link set to come up. So mylink.enabled equals true. Mylink.raw.enabled equals true. Now, that's about the most code you do in most of your programming, but I want to show you the process, and there's an example project attached to this application note that is a little more sophisticated, but it has exactly this listener built in. And what this does is when the ship launches, when the GUI launches, it runs this script, and it configures your UART and turns on your protocol. Okay, at that point, you are now ready to receive data and send data. So we're going to do something very simple here. We've defined iData to be a string. Let's make that a Boolean instead, just for sake of keeping things simple. And our OData will be a byte. Okay, so our input is a Boolean, our output is a byte. What we're going to do is we're going to wire up this logo to be a button, and when you press it, it's going to send a number. It's going to send a byte out the OData. Now this is a byte, and all we're going to do is count up And every time you press the button, it's going to send the next number. Very simple. So on the splash screen under the logo, I'm going to create a touch listener. So this is a listener, and it's going to be listening to touch0.event.e. And again, that's from the GRM, equals. So this is, and we're going to look for the touchdown. There we go. Okay, so this listener is going to wake up whenever you touch down inside the logo, and it's going to run this script. And this script, we're going to do something very simple. mylink.raw.odata equals 0x00. Okay. That is one line of code here. When I press on this logo, this listener will wake up, it will run that script. That assignment right there, mylink.raw.odata, by assigning OData, that is an output queue, that value 00 will go out that port, and you will see 00 come across the wire at 115K baud on your device. It's that simple. Now, if we wanted to create a counter, I'm going to add a variable, and I'm going to make this counter, and I'm going to give it a data type of byte, and I'm actually going to put this listener, and leave the listener there. I'm going to move the counter up just above the listener, and now what we're going to do is we're going to say, instead of 0, counter plus plus. So now, every time you press, it's going to send out the current value of counter, and it's going to increment counter. And it will roll around, and you'll get a negative value as it rolls around the byte because it's signed byte. But now you'll send a incrementing value out the port every time you press the button. Now, if you wanted to count the number of things that were sent, you can listen for an event on OState. So let's say we want to have right underneath this logo a little counter that shows how many items were sent. I'm going to add a piece of text. Actually, I'm a lot of text frame, and this text frame's top is going to be previous.utterbottom plus 1. So you'll notice how I've just defined this text frame right under here like this. I'm going to add a piece of text inside that text frame, and it's I'm going to say question sent. And I'm going to set it at the top center. So text, on my text frame, I'm going to say horizontal alignment centered. And there we go. So now we have this piece of text, question sent. Now I want to keep track of how many things were sent out the port. I'm going to add a variable that's going to count that. I'm going to give it a name, sent bytes, or sent objects, let's say, sent objects. I'm going to give it a data type of integer, so we're going to count as many as we ever need. And I'm going to add a listener under here. And this listener is going to listen to our OState. So I'm going to listen to mylink.raw.ostate. Now I want to listen to something for a specific type of event. I'm going to listen for the mylink.raw.removed event. You see that? This bigger here. So I'm listening for any changes on the OState, and when it changes, I'm going to check this condition. I'm going to see if it was the removed event. Now, this is very unique in SHIP, so be careful here. Normally, you only get change events or events in the system for listeners when something changes. This is one of the only places in SHIP where you will get a change event even if the value is the same. Let me say that again. You will get a change event on OState even if the consecutive values are the same. And why is that? Because if you put 3 things on the queue, the output queue, you will get 3 added messages. And you will get 3 events on the OState link variable, because you don't want to miss that. You don't want to lose one of those events. So it's really important that you understand that you will get all the activity on the queue, even if it's a repeated remove event or a repeated add event. So in this case, You're going to wake up when the output state changes. You're going to filter it and look for the removed. When you see a removed message, what is a removed message? That's on the output when it was removed from the queue and actually sent out the wire. You're going to get an event, and at that point you're going to run a script. The script you're going to run is, I want to increment this sent objects variable. So I'm going to say sent objects plus plus. So every time a new object goes out, it's going to increment this variable sent objects. Now, I want to change the text whenever sent objects changes. So I'm going to add another listener inside this variable, and this listener is going to listen to sent objects. And when sent objects changes, you can kind of see how it's chained here. It's kind of a chained interrupt type of chained event handler. I'm going to run this script, and this script is going to change the text. So I'm going to say text equals toString bracket sent objects. So that's going to take the number sent objects and turn it into a string. I'm going to add space sent like that. So whenever sent objects increments, I'm going to get a change event. It's going to wake this script up, and it's going to assign the text. So what I've done here is I've wired this so that when I press when I send an object by pressing the button, it's going to send it by shoving it out the wire. We're going to increase a count. That's only a byte. Whenever an object goes out, we're going to get this a removed event. We're actually going to get an added event and then a removed, because we put it on the queue and then it gets removed. In fact, we're going to get an added, and if we do it a few times in a row, make it a full. But in this case, we're going to get an added and a removed. This one is going to listen for the O state to change or remove. It's going to increment this variable sent objects. This guy's going to wake up when sent objects changes and update the text. So now I've got that completely wired, so whenever I press the button, it sends a byte and counts and tells me I got it sent. If I want to receive input, and let's say the input, where's our input? Our input was a Boolean, right? So our iData is a Boolean. Let's say I want the screen to be red when I get a true and green when I get a false coming in on the wire. So let's add a listener at the page level here. Let's go back here. Let's add a listener at the page level. Add new listener. And this listener is going to listen to mylink.istate. I'm listening to the input, or raw.istate. I'm listening to the input state. And when that input state says that something was added to the input queue, I want to wake up. And I'm going to pull that value from the queue. I can only do that once. If you need to remember what it is, you need to have a separate variable that remembers it. Because if you try to read that same variable twice, that iData variable twice, you're going to pull two things from the queue. Read once, get one. So if we add a script here, so let me show you what you need to be careful of. If I'm going to write this one way and then I'm going to write it a different way. istate mylink.raw.idata equals true, or false. Then I want to change my page's background color to red, right? So something like that. Page.bg color equals opaque, red, green, blue. Else, now this will work. Page.bg color equals 0x, opaque, red, green, blue. Okay, that's fine. That's absolutely fine. There's another better way to write this. Page.bg color equals, let's just take that, put that there, question mark, and then I can assign, if it's true, I want it green, and if it's false, I want it red. Okay, so that's obviously a very easy way to write that as well. Here's what you can't do. Now obviously you wouldn't write it this way, but this is to illustrate a point. If you do this, then the first, when it checks this if statement right here, if it will get something off the queue and say, is it false? If it is false, it'll run this and you're all good. If it's not false, you just fetched something from, you fetched a true, you fetched something off the queue, it's now going to check this one, it's going to fetch another one off the queue and check that one. That's not what you anticipated doing. So be very careful. You want to be careful about fetching things once off the queue. So I've done it very simply here, where I've just assigned it, but if you want to be super careful, then this is what you do. You say, my input Boolean equals, and let's just strip this back. What I'm going to do is I'm creating a temporary global variable or some kind of variable. I haven't created it yet, that's why it's going to give me an error. And I'm assigning that variable from the input queue. Now let me go back, it's going to give me an error, that's fine. And I have to create the variable, so I'm going to add a new variable, and we called it my input Boolean, right? Yep. My input Boolean, and I'm going to give it a data type of Boolean, and I'm going to put this listener inside it now, and I'm going to listen, and because I'm going to encapsulate it. So now I've got no errors. So now what's happened here is I've got a variable, a holding variable. I'm listening to that input state. When it changes and I've got something on the input queue, I'm going to grab it and assign it into the holding variable. Now I'm going to take and add a listener, and I'm going to listen to the holding variable. I can use the word variable, which means my nearest parent variable, or I could say my input button. I'm going to add a script, and in this script, I'm going to say, instead of checking directly my iData, because I already got it into the holding variable, I'm going to say my input Boolean. So page, BG, color, Michael. So now I've assigned it to this holding variable Boolean, and whenever it changes, I'm going to change the page background color. Now the advantage of doing that way is I can have other scripts that are triggered off that my input Boolean, and I won't be fetching multiple items from the queue. I'll have fetched it once, assigned it once. So that gives you an overview of how the raw protocol is wired, how you use events to make things happen. And once you've got that serial port configured through the initial script, you can see that these are one-liners. So you can move data in and out and do things with your device using the raw protocol very easily. Along with this app note are two projects. There's an A and a B project. It's designed if you have two SIMs and you wire them back to back across the UART. So 3-wire connection, ground, TX and RX, with the TX and RX swizzled between the two boards, that you can actually send bytes one way and strings another way and see it go back and forth. But if you just have one SIM, you should buy another. If you just have one SIM, you can load up either A or B, play with the project, and have it communicate to your device within a few minutes. I mean, you just light up the GUI, start pressing the button on the screen, it will start pushing bytes out the port. You should be able to see them on your analyzer or on your device. So enjoy.